In this example, we're going to show the inner product is homogeneous in the second spot. Now, conventionally, physicists assume that the inner product is homogeneous in the second spot, but we can make the argument using the mathematics convention. Okay, so let's just start out by being sure of what we're talking about here. We are talking about an inner product over the reals. So our inner product is going to take things from a vector space and we're going to map things from V cross V to the reals. So we're not going to worry about the complex numbers right now. Okay. And of course, we need to satisfy a number of assumptions to be an inner product. The first one is positivity. So the inner product of V and V is greater or equal to 0. And the inner product of V with itself equals 0 if and only if V itself is 0. Okay, property number 2 that the inner product has. The inner product satisfies UV, that's a V, is equal to VU. Now, of course, if we're talking about complex numbers, then this is the conjugate here. Okay, so it would be the inner product of UV equals the conjugate of VU. But of course, the conjugate of a real number is itself. The third property is linearity in the first slot. So alpha V1 plus beta V2 with W is equal to the alpha times the inner product of V1 with W plus beta times V2 with W. And finally, homogeneity, which is a direct consequence here. That alpha V and W is alpha times the inner product of V and W. Now, depending on what convention you're using, you might have 4 as a consequence of 3. You might have linearity in the second slot. Perhaps if you're a physicist, there's lots of different conventions for this definition. We want to show that the inner product, though, based on these assumptions, is homogeneous in the second slot. So what we really want to show here is that we need to show that the inner product of V with alpha U, alpha U1 plus beta U2 is equal to alpha times the inner product of V with U1 plus beta times the inner product of V with U2. Okay? So, in order to show this, we note that the inner product of V with alpha U1 plus beta U2 is equal to the inner product of alpha U1 plus beta U2 with V. And that comes directly from property 2. Now, from property 2, after using property 2, we can then use property 3 to break up our inner product into 2 different inner products. So we get alpha times the inner product of U1 with V plus beta times the inner product of U2 with V. This is property 3 that we've used here. And of course, what we're trying to show is that this is equal to alpha times the inner product of V with U1 plus beta times the inner product of V with U2. So all we need to do is reverse the order of these inner products, but we can use property 2 again to do that. So this is alpha times the inner product of V with U1 plus beta times the inner product of V with U2. And so this gives us exactly the equality that we need, that the inner product of V with alpha U1 plus beta U2 is equal to alpha times the inner product of V with U1 plus beta times the inner product of V with U2. So that's exactly what we have there.